Welcome back to the second installment of the AP ECE Chemistry Chapter 9 Liquids and Solids problem set. Let's take a look at problem number 19. For problem number 19, you're looking at a sketched out version down here of a phase diagram. Some information is given in the text about how your phase diagram should look. And so then after you kind of sketch out one, you are given some constraints and asked to decide which phase change occurs. So solid argon at 500 millimeters of mercury, which is about 0.67 atmospheres. If you look there, you're going to find that it should sublime when the temperature increases. So you kind of follow along, make the temperature increase, and you're going to see the change from solid over to gas right in there. For each of these other ones, the same sort of features occur. Solid argon at 2 atmospheres would melt when the temperature increases, so you're seeing temperature increase, you move across here, and that transition would happen from solid to liquid at 2 atmospheres, which would be somewhere in here. Argon gas at negative 150 degrees Celsius would condense when the pressure increases, so negative 150 would be, I don't know, somewhere in this range here. So you're going to get the change from gas up and through liquid. So argon at negative 165 would condense when the pressure is increased as well. So negative 165 would be somewhere in here, and it would, as you move up in terms of pressure, it's going to cross over the line from gas to liquid. For problem 25, you're asked to arrange a sample of diatomic halogens and their molecules in order of decreasing boiling point. So you got to consider intermolecular forces. All these things will be boring non-polar molecules. If you draw out their Lewis structures, it'd be 2 atoms connected by a single sigma bond with, on each atom, 3 lone pairs of electrons. So in each one of these atoms, they're going to look similar. In each one of these molecules, they're going to look similar because each of the atoms in them will look similar. And the only difference will be the size. So iodine has a much bigger size, therefore it has a bigger electron clouds, therefore it's more susceptible to dispersion forces. So iodine should have a higher boiling point than any of the other things because it's just simply the biggest thing. And it's going to be followed in order by bromine, chlorine, and fluorine. So fluorine will have the lowest boiling point because it has the least dispersion forces, the least London forces, which I guess can also be called induced dipole forces. Let's take a look at problem 29. Problem 29, you're asked to decide which ones of these things should show hydrogen bonding, and they give you some rough sketched out molecules or some chemical formulas for them. So remember, it's not really bonding, you're dealing with its intermolecular force here, hydrogen bonding, and you need to have a nitrogen, an oxygen, or a fluorine that's connected to a hydrogen. So here in this first molecule, you've got oxygen hooked to a hydrogen, it can have hydrogen bonding. Here you've got a nitrogen hooked to a hydrogen, it can have hydrogen bonding. Here you've got a nitrogen that's hooked to hydrogens, it can have hydrogen bonding. Here you have a hydrogen that's hooked to a fluorine, so it can have hydrogen bonding. Those are the constraints. Got to have a nitrogen, an oxygen, or a fluorine hooked to a hydrogen. Problem 35. In problem 35, you're trying to pick which thing will have a lower boiling point and explain. So you got to know a little bit about the different types of compounds, the different kinds of solids, and you need to know about your intermolecular forces as well. So for part A, you're comparing NaCl, an ionic compound, to PCl3, which is a covalent compound. So you want the lower boiling point would be PCl3. It's got covalent bonds. NaCl has ionic bonds. In order to actually get NaCl to melt, you have to break those ionic bonds. But in order to get PCl3 to melt, you don't have to break the ionic bonds. The covalent bonds. The covalent bonds exist still, but you would have to just separate the intermolecular forces. For B, you're comparing NH3 to ASH3, and you might look at ASH3 and say, oh, well, that's bigger, so it should, have a higher boiling point, and yada yada. But actually, it's going to have a lower boiling point as long as you pay attention to your hydrogen bonds. NH3 has the ability to make hydrogen bonds, so that's going to give it more intermolecular force. More intermolecular force means a higher boiling point, so the lower boiling point would be ASH3. If you take a look at part C, the lower boiling point will be the substance with the oxygen in the center of the molecule, not the one with the end hooked to the hydrogen. This first thing can have hydrogen bonding, this second thing cannot. And when you take a look at part D, you're comparing Hi to HCl, and HCl should have a lower boiling point. It will have weaker dispersion forces simply because chlorine is smaller than iodine.